one of the last sessions we talked about getting better estimators of standard errors for things using different types of estimators in the literature. So that was what the last session we did, was using the sandwich estimators. But in any case, no matter where you are with what model you're looking at, you can always use non-parametric or other resampling methods to approximate quantities or statistics that you want to estimate, even if you think that your models or your things are violating their various assumptions. So at the end of the day, if you have few tools left in the toolbox, or you know that whatever parameter, estimator, assumption you're making doesn't quite fit the data, you can usually get a good approximation of a statistic you want to estimate by using a resampling technique. Okay? So it's really useful to know how to use resampling techniques. And especially is useful to use resampling techniques. And we'll compare the resampling technique to the other estimators that just sort of come out of the box with linear regression, as well as the sandwich estimators we used the last time, and see how they compare and measure up to one another. Does anyone know what it means to sample with and without replacement?
Isn't that just taking numbers from like a group, and with replacement, you can pick it again?
Yes,
Okay.
correct. So sampling, Josh, are you familiar with this concept? Okay, so sampling with replacement means if I have a group of numbers and I want to create a random subsample of that group of numbers, I'm allowed to repeat values. So if I have the numbers 1 through 10, I'm allowed to take the subsample that is 1, 1, 1, 1, 1, 1, 1 if I specify that it has to be 10 long. If I specify it has to be 4 long, I can still have the value 1, 2, 2, 2, 3, 4 can be a vector, or 1, 2, 2, 3, or whatever it is. I can repeat those numbers. If I sample without replacement, that's called permutation. So I take a subsample, and that subsample is not allowed to repeat values. So if I say I can't get any other subsample, if I give you a vector that's 1 through 10, okay, and I say I want a 10 long vector that is subsampled, the only thing you can do is maybe swap the order, but it has to be the same composition of numbers if it's without replacement. But if it's with replacement, I can get anything in between. Okay, great. So the first thing I want to talk about a little bit is how we do that sort of estimation for simple estimators. So before we even work with the data, let's talk about a very simple parameter. Now, we're talking about regression coefficients, but at the end of the day, these are all estimates of various population statistics is usually what we're working with. So let's say we have some subsample of some normal distribution. And a normal distribution has two parameters, their mean and standard deviation, right? I just poorly drew where the mean is. Okay, cool. Now, my question is if I take a random subsample, suppose this is what the ideal population looks like. If I take a random subsample, i.e., you can think of any experimental data you acquire as a random subsample of the true population, right? Like, I don't have the ability to stain 5,000, 5 million slices. I've only stained 2 or 3 or 4 or 5 slices. I don't have the ability to sample 100,000 worms defecation time. I have only sampled like 10 or 8, whatever my population is. So that's a subsample of the real population that lives out in the universe somewhere, right? So my question is the mean of that subsample, whatever that is, the mean of the subsample, okay, what's the error around this mean in terms of how much it reflects the real mean, the mean of the real population out there? Like if I measured 100,000 defecation cycle things and I took the mean of that, how much is my random subsample of like 10 wild type animals, how much does it reflect the real mean, right? What's the error in that estimate, okay? So one way to estimate what that error would be is to do bootstrap resampling, okay? So what does that mean? That means if I have something like, so there's something else that we can use to estimate what that error is. That's called standard error of the mean. Okay, what is standard error of the mean? Does anyone remember offhand?
Standard error of the mean?
What's that? How's that defined? It just in a basic sample statistics case.
Confidence of the mean?
No. Standard error of the mean is defined as the square root of sigma squared divided by n, or sigma divided by the square root of n. So if you take whatever your sample standard deviation is, your SD, and you divide by the square root of the sample size that you have something that is approximately the standard error of the mean, or defined as exactly the standard error of the mean, but we believe that this is an approximate error to how off you are for whatever the real mean is. Okay? So in other words, how much do I believe that this mean of my subsample reflects the real mean of the real out there in the world? So obviously, what does that mean? As n, so what does that mean, right? So as n, if this is SEM, as n gets very large, this number gets very small, right? So what does that tell us? The more that we sample, the more that we believe the mean of that sample approximates. There's very little error in it anymore, right? The more we believe that that mean now approximates the real sample mean out there in the population.
Is there so like confidence intervals, like you're like X confident that your value is within that range? What about this? Like what's like your confidence?
Well, the confidence interval would just be the 95% confidence using this as the error.
Or so like the standard deviation divided by square root is the 95% confidence.
No, it's the standard error of the mean.
Or like so let's say you have like your sample mean and you have your standard error. Like how confident are you that the true population mean is within that range?
Right. I mean, you can design any confidence interval that you want, right?
Or technically this plus or so you have.
Okay. So hold on. Here's the real population. Here's the mean of the real population, and this is the standard deviation of that population. Okay. Now we take our subsample. Okay. And we have a mean of that subsample, and we have a standard deviation of that subsample. Okay. Now, what is the error around the computation of this mean? That's another normal distribution. Okay, that normal distribution has a standard deviation equal to the SD divided by the square root of n. So, what does that mean? Suppose n equals 10. So now this is the error in x bar. Okay, if standard deviation is, if the n equals 10, then this is whatever it equals, standard deviation by square root of n. So we have some error in the estimation of x bar. So this is the mean of x bar, right? The mean of that thing. And then this is the standard error around that mean, right? This is how much we believe this reflects this thing, right? But now imagine n equals 1,000, right? That's another normal distribution, except for it's a lot skinnier, right? Because it's standard deviation. This is why it's called standard error of the mean. It's the standard deviation of the error distribution around this statistic. Okay? It's the uncertainty in this number, as so far as it reflects this number, which is not the same thing, but although it's related to, but it's not the same thing as the sample standard deviation. Okay?
So technically, very technically, one standard error above and below the mean should encompass one standard deviation, so 68%?
Well, a standard error is smaller. So there are two normal distributions going on again. Okay. There's your sample distribution. Okay. And then there's your error distribution around the statistic of interest. In this case, maybe x bar. So that depends on the sample size, right? So if you have a really high sample size, that standard error is going to be really narrow. And if you have a really low sample size, let's imagine your sample size, well, 1 isn't really useful, right? But if your sample size was only 3, n of 3, then that's going to approximate whatever the sample standard, it's going to get closer to whatever the sample standard deviation is because you're dividing it by less, right? So as your sample size gets lower, that's going to get wider, right, at some point, right? And so plus or minus 1 standard error, so be careful about what language you're saying. Plus or minus 1 standard error of the mean refers to the uncertainty in x bar. So that's like from here to here. Okay? That is not the same as plus or minus 1 standard deviation. That refers to the variability in your actual subsample. Okay? that make sense?
Yeah. So that's why when I say you have your x bar,
Mhm.
and you do plus or minus one standard error of the mean,
Mm-hmm.
right?
That's whatever quantile degree of confidence it is around that estimate of the mean, right?
Yeah. So then wouldn't you say that?
I think it's like 67%.
Yeah, 68.
Yeah, whatever that is. Yeah.
So 68, you're kind of like 68% confident
That's
it's
where the
really-
real mean is.
Yeah.
Yes, correct. That's right.
Okay.
That's right.
I was at the beginning. I was wondering how confident you were.
Yes.
And that's
Yeah,
68.
yeah,
But
yeah.
no,
Right.
this, like,
And you can design a 95%. That ends up being like, what is that, like 2.6 standard errors, like something like that. I don't know, however, whatever the 95% quantiles are.
Yeah.
It's like 2 point something. I don't remember exactly what, 2.5, 2 point something like that. I don't remember.
I thought it was 1.96, but
Is it 1.96?
I honestly
1.96 is for a T distribution.
Oh, okay, is that what it is? I just remember
Sometimes.
the number. I saw that
We
number,
can,
I was like,
it might be 1.96. Well, actually, we can figure that out right now. How do we figure it out? It's from the standard normal. So what are the quantiles of the standard normal, where the probs are C equals 0.025? Oh, I don't have a 5 either. No, you have to understand, my laptop. Well, no. The thing is, I noticed that eventually, I'm just going to copy 4, 5, this, and percent sign, and put them somewhere in here.
At least your
So that I have
Control
them.
C and Control V is working.
Well, 5 and then 0.975, okay, where it's a mean of 0 and a standard deviation of 1, because that's the standard normal. Unused arguments. Hold on. Oh, it's just called P. Okay, yeah, it's 1.96, you're right. 1.96. So it's 1.96 times whatever your standard error of the mean happens to be. Okay? Technically speaking, in frequentist statistics, I should correct this before anyone drags me on YouTube. In frequentist statistics, that is not what a confidence interval means. That is the definition of a Bayesian credible interval, which this is why I hate statisticians sometimes, is because for most intents and purposes, those two things end up converging on the same thing, and they mean the same thing. So at the end of the day, you can pretty much interpret it with the meaning that you are however much sure you are if that's where the mean resides. Technically, in frequentist statistics, the definition of a confidence interval is a little bit more nuanced. It's 95% of the time, if you constructed an interval this way, it would contain the mean, which is annoying and makes your head want to cry. But for linear regression, it turns out that the frequentist 95% confidence interval and the Bayesian credible interval converge to being the exact same solution. So for all our purposes, you can interpret the confidence interval as the uncertainty that you are with respect to that parameter. Okay, so you are 95% sure that that's what the parameter value is. But statisticians will fight back and forth about the particular nuance of that meaning. That's mostly a philosophical orientation, but anyway. Okay, cool. So you can calculate the standard error of the mean a couple ways. One way is oh my god. There we go. Doot. So one way is to take your mean and plus or minus SEM, where SEM is defined as the standard deviation of the sample divided by the square root of n. That's cool, you have that. Great. The other way to figure out what this is to do a resampling technique, right? So how would you do that? So you have your sample, let's say n equals 100. Okay, so let's say you do a population of 100. So how do you determine the error in the means estimation? So the first thing you do is you have your mean, so that just equals whatever the mean is, right? But then you do a bootstrap. So basically you say for I equals, or let's do it in R speak, for I in 1 through n boot. So however many times, how many simulations you want to do? Only 10 simulations, wow. Really liberal here. Okay. Typically for publication, I do 10,000 to 100,000 simulations. But we can do 10 to the third. did another third simulations. He only wants to do 10. He gets his reviews back from them. They're like, you only simulated this 10 times? Okay. So you do this each time, but let me finish first. Okay. And then what you do is you take it. So let's say this vector is called x, and that has 100 things in it. That has all of your population values in it. So you take an xk, okay, where the length of k, whoops, equals 100, okay, but you're sampling with replacement, which means you can have index number 1 a few times in a row, and you can have index number 2 and 4 and 5 and 10 and 10 and 10, so on and so forth. You figure out what those values are. You calculate the mean of xk, right? And you store that value. And then you repeat that this number of times. So each time you take a subsample, calculate the average of that subsample, and you keep doing that over and over again. Then that gives you a distribution for the mean. It gives you a distribution for how you've calculated the mean. So let's actually do this from the console a little bit.
By the way, if you do a bunch of, so each time you do it individually, that's bootstrap, right? Resampling with replacement. And then if you do a lot of times, is that when you're doing bagging? What's the difference between bootstrap and bagging?
No. Bagging, I think, stands for bootstrap aggregate. So when you do, this you might want to look up to be certain, but that is when you do a bunch of it's creating like an aggregate estimate based on all of those bootstrap samples.
Or what we're doing right now?
Sort of. Is it the same? Let me look this up and get back to you.
Sure.
Let me look it up and get back to you.
Sure.
I think that I don't want to say those two things are the same. I'll just say that. I guess in a sense it is very similar, but that's for a single. So in this case, I'm going to keep the whole bootstrap distribution, and I'm going to say some things about the distribution. I'm going to say what its average is. That might be the output of a bag. The output of the bag might simply be what is the average of all the bootstrap samples. You're done. That's a parameter. Now you have that parameter. Go off and live your life. In our case, I'm going to keep the entire bootstrap distribution because I'm going to determine other things about it. I'm going to determine the standard deviation of that distribution. That's going to be my empirical standard error of the mean, right? I can determine the variance in that distribution. I can determine the 95% confidence interval of that distribution. I can determine a bunch of things about that distribution and keep all those data points, which is why I'm not calling it bagging, because to me what bagging means is that at the end of the procedure, I come up with one number or one answer or a vector of answers or something like that. So I just think it's what the output is. In this case, I'm not discarding the rest of the things in lieu just to get the single answer. You know what I mean? Okay. Anyways. So let's go ahead and do this real quick. I'm going to go ahead and say, let's call this A, and I want you guys to do this along with me. So we're going to pick a random subsample of numbers. So we're going to use the normal distribution to do this. In R, all of the distributions, if you want to pick random numbers, you start with the letter R, and then it's the name of the distribution. So random numbers from the normal distribution is R norm. And then you say how many you want to pick. So let's say n equals, I don't know, let's pick a small number. Let's pick 20 with a mean of 15, oh no, and a standard deviation of 2. I'll just say we did that. Okay, so you can go ahead and run that. And we can inspect A from the command line. There's A. This is my A. Your A is going to be different because we have all different random number generators, that kind of thing. So we have this. Okay? And I can calculate some things, like I can calculate the mean of A. The mean of A is 15.2. I can calculate the standard error of the mean, right? What is that? That's SD of A divided by 20. 0.0. What's up?
Square root of 20.
I'm sorry?
Square root of n when you
Oh, thank you. My bad. Thank you. Yes, thank you. 0.4446 or 45. Whatever. I saw the 6 afterward and I said it. 0.45. Cool, we have it. So I'm just going to go ahead and keep this value for reference. So so the sample standard error of the mean is the value of 0.4464. Oh my gosh. All these things I can't access. Yeah, it's time for a new computer. Okay, this value, okay? Now let's go ahead and do a bootstrap to determine the same quantity. So how would we do that? I'm going to say, let's create a vector where we're going to store everything. Let's say n boot equals how many times we want to do this. Let's say we want to do it 1,000 times. Let's call it that. And I'm going to initialize a vector to store the values of the means that we calculate. So I'm going to call that boot means. And to initialize this, I tend to just do it this way, which is I just repeat the value of NA for the number of times that I'm doing something. So you can see that nboot is you can see that boot means is currently filled with a bunch of NAs, and then for each iteration of the loop, it'll fill in all those values. Cool. So what I'm going to say is that for I equals 1 through nboot. Okay, so in our syntax for a for loop, you put the condition of the loop in normal parentheses, and then you put whatever is going to be the functional part of the loop in curly brackets. Okay. Oops, except for that's not equals, that's MATLAB speak. It's the word in. There we go. Okay, for I in 1 through nboot, curly brackets, there we go. So now what are we going to do? Let's create our subsample, so we'll call that k. And we're going to use the sample function, so sample. Okay, now what is the length of the sample that we want to return? Well, what are the number, how do we want to choose the sample? To choose the sample, we have to pick from the indices of the vector, right? So our vector is 20 long. And I want to pick a sample like 1, 1, 2, 5, 10, 2, 20, whatever, to like pick from that thing. So I'm going to create a vector which is 1 through the length of A, right? Those are all the indices, because remember R is 1 index. So those are all the indices of A, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to pick a sample from this. Okay? Alternatively, well, there are a couple different ways to do this. I can actually directly sample from, there are two different ways to do this. The reason why I'm doing it this way is because I want to show you how to use this indices for a different function called the boot function later. But for now, I'm going to do it this way. And then I'm going to say that I want to create what length of a sample. Well, I want to create something that is the length of A. So I want to pull a subsample that is the length of A. With replace equals true. Okay. So what will this generate if I do this once right now? There, it's generated a list of indices. You can see it repeated the value 3 2 times. And all this stuff. Okay. So it's going to create a vector that's going to pick from our original A up here, but it's going to choose these index values. Okay? So now I can calculate my mean is the mean of A where the subsample is K. So what does AK look like? Okay, so again, just to remind you, here's A, right? So AK is the same length, but it's the indices that we've chosen. Well, oh my gosh, I forgot to do that. So now AK looks like this. So again, I don't know what K was in this case. Let's see. It looks like it repeated. Did it repeat any values? Well, you'd have to do this a lot of times to start seeing it repeat. I got lucky that other time. Let me do it again and see if it repeated some values. Oh yeah, here it repeated 15 a couple times, right? So if I do this, whatever the 15th value is should be repeated a few times. And it looks like we got it here and here. So one of these values is repeated a couple times. Maybe it's this, yeah, 13.90734 is repeated a few times. So let's pick this sample. So now I'm just going to calculate what the mean of this is, right? So what's the mean of that subsample, or that resample, rather? That's 15.14. Okay, how does that compared to the mean of A? Well, the mean of A was originally 15.02. Okay? So it's close, and we would expect that to be the case. So if I go ahead and run all of this, what I'm going to say now is that I'm going to specify that my boot means I, so my ith boot sample here is going to be the mean of AK, right? Does that make sense? Hopefully that makes sense. So every time I do this, so for number 1, we'll do this. For number 2, we'll do it again, and do it again, and do it again, and do it again for 1,000 times. Okay? So this should run fairly quickly on everyone's computer, so go ahead and run it. I finished on mine pretty quickly. So now if you do a hist on boot means to create a histogram, you'll see this. This is the bootstrapped error distribution around the mean of all of those samples, right? So what is the mean of boot means? It's very close, but not exactly the mean of the original A, right? So the mean of, it's very, very close to it, but not quite. So it's centered on right about 15, and this is the error distribution around that, okay? This is different, of course, from the hist of A. The hist of A looks like this, because this is our actual original sample. So this is showing you the error that is believed to be around this estimate if you resample 1,000 times. Okay, so this is the original data, and then this is the bootstrap of the mean of the data. Okay? Does that make sense? So again, this is a histogram of the original data. The original data has all sorts of values. It ranges, looks like, between 11 and like 20. It has an average value. That average value is around 15. And if you resample 1,000 times, you get a distribution that looks like this. I'm going to change this to 10,000. I think that should run pretty quickly, because it's not like fitting a model. It's just calculating an average. You know what I mean? Whoops. And it looks like this. So I'm going to compare what happens to this histogram if I make it like 100. It might not change that much. Okay, here's 100. Here's 1,000. And here is 100,000. No. Yeah. That's the right. There we go. Okay, so what do you notice about each time that I do this? Exactly, which is exactly what you expect. And that's the basic theory behind standard error of the mean, too, is that the more and more and more and more you resample, the more and more and more precision you're going to have around whatever that estimate is going to be. Which is approximating what you would do in real life, which is actually sample more and more and more and more and more in the population.
Wait, standard error of the mean.
Standard error of the mean scales with n.
Sorry, it has to do with or without replacement, or doesn't matter?
Standard error of the mean has nothing to do with resampling techniques. Standard error of the mean is a theoretical quantity.
Oh, okay.
It's standard deviation divided by the square root of n. It's based upon the principle that if we went out there in the population and I sampled 10 times more people, I would have a more precise estimate of the mean, which kind of makes sense, right? And if I do that, my simulation of doing that is doing the bootstrap. So the standard deviation of this thing is the bootstrapped estimate of the standard error of the mean. Right? Does that make sense?
A lot of words, but slowly.
Okay, what is the bootstrap distribution showing me?
It's showing you if you redo your sampling, or
What is each value in the bootstrap distribution?
oh, it's the mean of when you
Correct.
resample.
Correct. So it is a population of means.
Yeah.
Okay? So that's why the standard deviation of that represents the standard error of the mean. Does that make sense?
Yeah.
So this is the distribution of what the mean looks like every time you resample. So the theory behind the theoretical quantity standard error of the mean is that if I go out there in the world and I take another subsample, or I take a larger subsample, or I take an even larger subsample, okay, and calculate the standard deviation divided by however much I've scaled it to, that is my precision or my uncertainty in my estimate of whatever the mean is. You can see that here, it's the same thing. If I resample 100,000 times, I have a more precise estimate of that mean. Okay, so the tightness around this distribution kind of scales with that. You don't really notice that, like, it looks like there isn't that much of a difference between 1,000 in terms of the endpoints. Like between 1,000 and 100,000, we didn't really gain very much. Probably because we have a relatively small, I mean, there's only so many simulations, there's only so many resamples you can do. But between 100 and 1,000, that's obvious. So this starts to extend below, like closer to 13 and above 16, which goes away once you get to 1,000. You're starting to have the bulk more around the 15 and stuff like that.
So you assume your original sample is like your population.
That's all you can do, because when you resample, the whole reason why you do resampling techniques is because maybe you don't have the ability to do more sampling out there in the wild, or alternatively, you aren't so certain that a theoretical quantity represents the real uncertainty that you think you have. In other words, you aren't so certain that the assumption that you can take the standard deviation and divide it by the square root of n is applicable. It might not be applicable. Additionally, resampling allows you to calculate any quantity you want. What that means is you can even calculate uncertainty around quantities for which there is no theoretical definition of what the uncertainty would be, right? Which gives you access to things that violate any kind of rules that you would expect in a lot of modeling parameters or modeling statistics, right? If you have a new definition or you have a distribution that has all sorts of crazy error variances in it or all sorts of other things, resampling is a technique that you can potentially use to determine the uncertainty around a statistic of interest if you don't have access to a theoretical quantity that is applicable to you at all. So me assuming that standard, now in this case, we chose A from a normal distribution, right? So my hypothesis is that this sample standard error of the mean, 0.4464, is going to be very close to whatever the standard deviation of this thing is. So let's find out, right? So in this case, I did n of 100,000. What's the SD of the boot means? Well, lo and behold, look what it is. It's 0.43 in my case. I don't know what you have. Josh, you're looking confused.
Oh, no. It's just that yours is more accurate. But
That's because I did 100,000.
Yeah, I did 10,000.
Right, if you do, so okay, so again, here is the SD of A divided by the square root of the length of A. This is the theoretical standard error of the mean, 0.446. We think that's the error of the mean. But if we do our bootstrap, let me go ahead and just do SD of boot means and have it report that. Let's do it at, let's start at like 100. Let's see what that looks like. 0.48, so it's close, but a little bit far off, a little bit further off. Here's 1,000. Probably will get closer. And remember, every time I do this, I'm going to get a different value, right? 0.42, 0.425, 4.22, 0.444. So it's vacillating around 0.43 something. So every time you do this, you can get an error about the error. Every time you do another resample, you get an estimate. You can have an error estimate on how much you believe the error estimate. You daisy chain it forever and ever. And if I do 100,000 or 10,000 one last time here, doop, 0.436. This is actually very close, 0.444. If I do it again, it's probably going to vacillate 0.435. Actually, it looks like it's stabilized right around 0.434 something, 0.3 something. Yeah, it likes that. Oh, it went up a little bit. Anyway, you can get more reproducible results from your random resampling if you set your random generator seed at the beginning of your code each time. Okay, cool. So that is bootstrap resampling for a simple quantity like a mean. Now, when you bootstrap something I'm going to show you is that we're going to bootstrap Maddie's data, okay? But let's think about this. For her data, we have a value for the defecation time for each animal, and we have an age time point, and we have a genotype. When we just did resampling here, we randomly resampled within that vector A. But if we don't respect the hierarchy that's in the data, we're going to mix mutants and wild types together when we resample, which is going to throw all the estimates for individual groups off, which we probably don't want to do, right? So you can code that up to be respectful of that. Basically, you say, okay, so for each interaction of age and condition, now I want to resample just in here. And then do this and do this and do that over and over again. That's a lot to code. You can do it, but it might be messy. It might be a messy nested loops kind of situation. You could do it. It wouldn't be that hard. We can use the boot library in R to do it much more simply. Okay? So in your preamble here, I did the library boot thing. Did you might have to install that if you didn't load. Did it give you an error when you tried to load it? Try to load library boot real quick. Mine just looks like this after I run it. If it gives you an error, then you're going to have to install the package. You're all good? Okay, you have it installed. Fantastic. Cool. So using this, we can actually respect the order of what we want to do. Okay? So what we are going to do now is we are going to bootstrap the linear regression model. What does that mean? Okay? I'm going to describe what that means in here real quick. And then this is the last thing we do. Like, this is one of these things that like isn't too, like, I don't mind taking a little bit of time to go over it in depth, because it is a very useful technique, especially for when you move beyond linear regression. You're going into like empirical models, or even for some of your machine learning things like neural networks and other things like that. Like, it is useful to have some resampling techniques to get better estimates of things. You can imagine resampling, refitting everything, regenerating predictions, and then bagging would be taking the average of all those predictions and reporting that as your real prediction. Right? That's what bagging is to me. Okay, so anyway, here we have data. So we have some y value, and we have some parameters. We got age, and we got genotype. So every row is a worm. So it's got a value for these, all these things. So what we want to do for our algorithm, so normally we fit, right? We do this. And then we get a list of these beta values for like each interaction of things or whatever. What we want to do is we want to resample D respecting the hierarchy. So what do I mean by that? Suppose we have wild type at time point number 1, and this is animal number 1. I'll just do 3 because otherwise it's going to take me forever to write this. And here's mutant, time point number 1, time point number 2, time point number 3. Okay? Okay, suppose this is our data. We have n of 3 for each. If we do this thingy bobby, we're going to end up with just, I mean, it's just 2 coefficients. It's just a simple system with wild type and mutant, right? To do the bootstrap, to get bootstrap samples for each beta, what you have to do is you resample, but you respect the categories. So that might mean that one of your, here's I equals 1, okay? Maybe we got 1, 2, 2. Like, this is our resample. Respecting the hierarchy means we don't mix the mutants in with that group when we take that resample. We leave the labels intact. The labels are intact, which means we can't just take the index, like, we can't just say, okay, if this is the index 1, 2, 3, 4, 5, 6, I'm not allowed to have a vector that is 1, 2, 4, 4, 6, or whatever. Like, I can't make that a resample without respecting these labels. We have to sort, we have to keep the labels associated. Otherwise, when we fit, all of these betas are going to end up being like 0, essentially, because we're mixing all the categories together. Imagine if you had an actual, if it was a slope, like a time course, and you didn't respect the time points, you'd completely lose the relationship structure in the data doing this. So we do that, so we end up with this resample for this one, and maybe for this one we end up with a resample that is M1, M13, M13. Now, mind you, if you only have n of 3, this is going to have limited utility, because there are only so many resamples you can do. If you only have 3 things per group, I can only do 1, 1, 1, 2, 2, 2, 3, 3, 3, 1, 1, 2, 1, 1, 3. But you can't, if you want to do like 100,000, eventually you're going to hit a moment where you can't make any new you're not gaining anything by doing this. So n of 3, maybe not that useful. There's a sweet spot where you need to have at least a certain amount of n probably for a bootstrap resampling technique to like give you much advantage, right? N of 3 probably not that useful. But we end up with this, then take this is our new resample data for I equals 1, and refit this and it outputs coefficients, right?
So you resample within each group?
Correct.
Basically?
Correct.
And when you do that, do you have to respect like the order, or you don't care?
Well,
3, 2, 1?
sure, no, the order part doesn't matter. Unless for some reason there's some sort of order structure, there's another factor in your data that has things ordered, like a time point or like something like that, right?
Are these not time points?
There are, but that's a category we're considering. We're only resampling within wild type time point number 1, in which case there's no order to animals, right? They're just animals and wild type at time point number 1. Now, you would, in order to make sure, that's respecting an intersection of 2 different categories, right? That's respecting the time point 1 and the wild type. So whatever your lowest common interaction between 2 categories is the one you have to respect. If you had 3 categories, like 3 time points, 2 drugs, and 5 groups, you'd have to make sure to resample within each combination of group, time point, and drug to make it make sense, right? But then you do that, you refit the model, you output your parameters, okay? And then what you'll end up with, is beta 0 being a vector of beta 0s, right? And beta 1 being a vector of beta 1s, which are all, well, I really can't draw straight today. Beta 2, I'm just, a vector of beta 2s, where you'll have this big matrix where across the columns here are all of your individual resamples from 1 through n boot, right? And then the average of these, the average of each of these vectors the average of the mean of beta 1 should be pretty close to the original beta 1 from the model, or the original beta 0 from the model. But now you're going to have a standard deviation of this, which is the standard error in that beta, right? Determined from bootstrap resampling, right? Cool, great. That's what we're going to do. So I'm going to show you how to do that. So to do that, the first thing we're going to do is we're going to fit our model. So our model, remember, is LM. In this case, it's defecation cycle as a function of age, or condition times age, where the data come from D. Okay? So there is the model. These are the coefficients, where the intercept is the time point number 1 for the wild type, and these are all various offsets. Cool. This is the basic thing that we've done probably a bunch of times. That's cool. Now, what I'm going to do is I'm going to write a function. This is the first time maybe any of you have, Josh certainly, but maybe Maddie, I don't know if we've written functions before. But I'm going to read a function. I'm going to write a function called pull coef. I don't know. I'm just going to pull the coefficients. And I'll describe what this is going to do later. Okay, so in R, to write a function, you give it a variable name. So it's just a variable like any other. But then we say it's a function. And in the normal parentheses, we're going to put whatever it's a function of. Okay, just like a for loop. And then in curly brackets, we're going to put like the operations that we're going to do. So to make a function, you need a condition for the function, or the parameters you're going to pass to it, and curly brackets. Okay? So we're going to give it 3 things. We're going to give it a formula. We're going to give it some data. And we're going to do a last thing called k, where k represents the subsample that the boot library is going to determine whatever that subsample is. Okay? So the first thing I'm going to do in my function is I'm going to say that data temp, let's call it, equals data, where the rows are now resorted according to whatever boot has determined k is going to be. Okay? So it's going to determine the permutation on all the groups and all the things. Maybe that's index 1, 1, 1, 1, 2, 2, 3, then 4, 5, whatever it said it is. We're going to reset the data based upon that k, whatever that k ends up being. Okay? Then we are going to fit a model. So model temp is LM, the formula where the data come from data temp. Okay, so we're going to refit the regression model. So data temp here is our resorted data for the resample. And model temp is just whatever the refitted model is. Okay? And then we're going to say the coef temp is the coef of model temp. I'm just writing it in a very, I could write this like kind of all in one line, but I'm doing it in multiple lines for clarity. Okay? And then in a function, in R, you always say what you're going to return as the output of the function using the return function. So return coef.temp, which will be just the vector of the coefficients. You could see how I could do this all in one line easily, right?
I think it's funny to me how return is a function in itself.
Yeah. Return, but as you can see, the inside of my function, I'm calculating 3 different things. So I want the output of this function to be this, right? So in general, you don't have to type this. I'm just going to show you what this does. Suppose I had a function f is the function of x, where we're going to return the value x times 2. It multiplies something by 2. Obviously, I don't need a function to do that. I can just type 2 times the thing, right? If I do this, what does this mean? Now I can do f of 2 is 4, f of 10 is 20, f of 100 and whatever that is, 1,000, 1,111 is 22222. Okay, so it just multiplies 2 each time. Return is telling it what to return. By the way, this is fun about R. I don't know if you could do this in Python. In R, within this part of the function declaration, you can specify what the default value for every variable is. So you can say x equals 6. Okay, you can do that for Python. You can't do it in MATLAB.
Oh, really?
It's very annoying in MATLAB. So you can do the same thing. You can say that if I don't give you anything, okay, I can say f is 12 because it knows the default value is 6. So it's just handy. In this case, this is more complicated, right? So this, in this case, pull coef, well, if I just did this, I don't need you to do this right now, but I'm going to go ahead and if I run this, if I hit Control Enter, then pull coef will appear in my workspace under functions. Okay. So now if I do this, okay, if I say pull coef using the formula of my model, using the data just equal to d, and k equals just 1 through n row of d, so just the order that that it already is, all it's going to do is pull the coefficients as they are. Because I haven't done anything, right? I haven't resampled d at all. All it did was reset this, fit the model again, and pull the coefficients, right? But now the idea is that every time I do this, I'm going to have a new resort for whatever k is, and it's going to output new coefficients. Okay? So now let's go ahead and do the bootstrap. So make sure to run your function so that pull coef exists in your workspace. So now I'm going to show you how to run the bootstrap. So I'm going to say, let's call it boot run. I don't know, call it whatever you want. Equals, we use the boot function, very simple. Okay. This is a lot simpler than doing all of that nested loop business. So the first thing, what am I going to give the boot function? First, I'm going to give it what it is that I want the boot function to do. Okay, that's going to be, it's called the statistic parameter. And that I'm going to say is the function pull coef. That's what I want it to do for each run of the bootstrap. Okay, cool. The next thing I want to tell it is where the data come from. I want to tell it what, basically, see how in this function I have to give it 2 things, one thing called data and one thing called formula? Okay, I have to give those things to boot, so boot passes them on to pull coef. Okay, so data, well, that's just d, that's easy. The next thing is formula. Well, that's just the formula that's already in the model. I could type out defecation cycle equals condition times age again, but I can just pull that because if I do this, that's this already. So it's just there. Okay. So I'm going to give it the data and the formula. These are the 2 things that I need for here. This k I don't need to tell it because that it's going to use as my like resampling index value thing that it's going to determine what that is each time. And it could be called anything. You call it I, you call it j, you call it anything you want. Okay? The next thing I'm going to give it to it is how the hierarchy in D is specified so it knows how to respect it. Okay? So that's called strata. So how do I do this? We got condition and age, right? So we want to respect those 2, the interaction of those 2 things. To do that, I'm going to use the interaction function. I got to copy my $sign. Where's my $sign at? Up here. So it's condition and age, right? So D condition and D age. What does this do, by the way? If I just ran, you don't have to do this, but just to show you what this does, if I run this from the command line, all it does is it creates a new factor that is just the labels are like these separated by a period. So it's creating the individual subgroupings, because otherwise it's like two different variables. So this is the strat it's going to respect. The next thing I'm going to give it, whoops, and is R. And R is the number of bootstrap things I'm going to run, the number of reps. That's inside the boot library. They decided to call that word repetitions or reps or whatever, replicates of the thing. So how many do we want to run? Let's just do 100 for now. But you could specify, and you can see how it changes if you like do different ones. Okay, cool. So I'm going to go ahead and run this.
So you don't have to pass in arguments for pull coef?
For what?
For pull coef?
They're right here. So what is this going to do? This function is saying for each of 100 times, it's doing all the nesting for me. So say says k equals I equals 1. Okay? It's going to figure out a k that it's going to use. And then using the values that I've given it for data and formula, it's going to pass those right into pull coef.
You don't have to use like extra parentheses?
No.
Oh, wow. Okay.
Yeah. It knows because basically, see these two parameters in here? Those aren't parameters that are built into boot. In R, you just daisy chain whatever other functions that are built into a thing that you pass in as a parameter. Whatever it needs, you just add them on with commas.
Wow.
So it's handy. It's convenient. So it's right there. So I'm going to go ahead and run it. And it's done because it's only 100. Okay? So hopefully that worked for everyone without a crash. Cool. So now we're just going to explore the inside of this. Okay? So boot run has a bunch of things in it. This thing, it doesn't output just a matrix. It outputs a bunch of things. So it's a list of 11 things. Okay? The most important one of these is this T matrix right here. This has 100 rows and 12 columns. What do we think that is?
100 different samples? Or
It's dimension. So there are 12. I'll tell you, there are 12 coefficients. So what is this matrix?
all of your coefficients?
From each bootstrap run. So it's got 100 rows, meaning we did this 100 times. So each row is that. So if I did a head on boot run $T, you'll see what it is. It's each of the coefficients, okay? And then down the rows are what? The values that have been determined for each bootstrap. So like, for example, this column, one of these columns right here, here we go. This column I can almost, 1, 2, 3, 4, 5, there it is. This one right here. Number 4, I'm almost positive, is one of the Norexin mutants that has an increased effication time. This is coefficient that represents the change in time from that to wild type. Down the rows are what the value is after each resample. So you got a 21 and a 20 and an 18 and a 20 and a 21 and a 23 and so on and so forth. Okay? What's up?
So like a fairly random question.
Hmm?
Obviously, when you're doing bootstrap and you want to sample from a normal distribution, or it depends on your problem.
What do you mean?
Like
We're not sampling from a normal distribution. We're sampling from our data. Oh, you mean what?
Like a uniform distribution.
It's using a uniform distribution. I don't know if you can change that within the boot function, and I don't know how that's determined. But there are other parameters you can pass to boot. You can look at the documentation. So you can probably pass, there's different weighting functions you can add to it to how it resamples, and you can probably choose a different way to resample. But I think that it is just using a uniform distribution to resample.
But usually you want to use a uniform distribution.
Probably.
Yeah,
That makes the most
why-
sense. Yeah, unless there's some weird thing in your data that there's a reason why you want to mostly resample some values versus other values. I don't know why you'd want to do that though.
And like from like just like staring at like not this specific thing, but just thinking about it,
Mhm.
like the things I could think of off the top of my head in terms of why you want to resample with replacement is if your data, you can't sample the entire thing in the world, but
Right.
also it kind of gets rid of outliers in your data.
That's right.
Is there another thing? Other?
Well, it certainly gives you the ability to run more simulations.
Uh-huh.
Now, depending on how much data you have, so let's consider this. A regression model isn't going to like it very much if you have a resampled group where every single value is an identical value,
Yeah.
right? That's not going to work. That probably will turn up an error because there's no variance in that, right? When you have enough data, that resample is extremely unlikely unless you resampled millions and millions of times, right? So you do have a limit to where like how much you can resample is somewhat limited by your data. With enough data, look at D. D has 109 observations in it. Each group has at least 10 to 12. You've got a lot of leeway for how many different resamples you can use without ever reaching the probability of seeing the 1, 1, 1, 1, 1, 1, 1, 1, 1, like it's all the same number. Like that's pretty unlikely. But if you only had n of 3, that would be a lot more likely. So at some point, there's a trade-off there. Obviously, let's consider if you don't use replacement. If you don't use replacement, there are only so many permutations of an n of 5 or 3 that you can create. So you can only really resample so many times to like generate that distribution. But in general, you're right, it smooths out the effects of outliers for sure. Yeah, additionally, it's just a nice way to get an error estimate on some of these things when you think that your data are violating a lot of the basic assumptions of whatever the regression model is going to do. Because remember, what does the regression model expect? That when you have different levels, you have an assumption of homoscedasticity. That's the assumption that within each group, the variance is the same. We know that's not true, probably. In a lot of cases, it's going to violate that assumption. Bootstrapping is a way to not avoid having to avoid having to assume that. Because when you resample and you refit and then you calculate the standard error, like the standard deviation down each of these columns, that's not making that assumption at all. It's just whatever the fit decided to output, right? So it's a useful technique for these cases. So now what we're going to do finally, just in the last couple of minutes, is I'm going to compare what the standard errors look like if you did it this way versus if you did it using the built-in regression model assumptions versus that other like literature estimator that we used the other week from the sandwich package. Like just compare all three of them and see what they look like. Okay? So to do that, let's go ahead and let's output the coefficients. So the boot coef, that's equal to the boot run. It's that T matrix. Okay. Cool. And I'm going to go ahead and put the names on this just for completeness. So I'm going to say the col names of boot coef equal the names of the coef of the model. Okay, I like to keep the labels on things because that way you know what you're looking at. So if I did a head on boot coef real quick, you can see now all of these columns are labeled. Right? Okay, so you should see that. Great. So now I'm going to create the variance covariance matrix of this thing. Okay? Call that boot VC. Where down the diagonal are the squared standard errors of each of the columns. Okay? All that is cov. You use the cov function for this. And then you have to transpose this because it expects the rows that it's comparing, or like the squared terms to be on down the row. It expects what we have as the columns is down the rows. So I'm going to transpose it by putting T boot coef. Okay, so boot VC should be a 12 by 12. Okay, and if you look at boot VC, it has all these numbers in it. Well, that's ugly. That's cool. But importantly, the diagonal of boot VC has the ooh. No, wait, hold on. Did I do this wrong? What did I do? I thought it needed it to be transposed. Maybe I'm wrong about that. Maybe it's just, hold on. Dim. Oh, okay, never mind. Just kidding. You don't have to transpose anything. I thought you did. So just cova boot coef. That's enough. So if you look at boot VC, it's a square matrix where down the rows, and we'll worry about the off-diagonal terms some other day, but down the rows are the squared standard error terms, the squared variance terms down each of those things, right? Down each of those columns, okay? Great. So we're going to use this in our estimation of things, okay? So let's go ahead and compute all these things real quick. So to do this, let's go ahead and let's make an exemplar data set. So I'll say X data is expand dot grid, where we create a label called condition, is the levels of D condition, and then age is the levels of D age. What does this do? This just makes my thing where I want all of these values, right? Where I have wild type, I want to get the predicted values for the means and the standard errors for like each of these things, right? Remember this expand grid function, we've used it a few times now. It's just an easy way to create a quick matrix or a quick data frame that has like every possible combination of each thing for us to do prediction on. These are the values we want to get the predicted values of. Okay. And then what's our X matrix? That's X is model matrix condition times age.
By the way, you wrote a matrix.
Thank you. So this is our X matrix that we need. It's got the ones and zeros and all the things so we can do our calculations. Okay, so now let's say X data dot, or rather defecation mean, we'll call it, is X. I need my percent sign. Percent sign star percent sign coef model, right? So this is the expected value for the mean of each combination of groups, right? Great. How do we calculate the standard errors of all those things? Well, there are a few different ways. The first one is we'll call this the linear regression all assumptions fulfilled. Let's call it that one, okay? So, X data, oh boy. Let's call this SE, standard error, okay? Is equal to the square root of the diag of X. This is the mathy part. Sorry, guys. VCOV model dupe transpose X. This is the assumption of linear regression. Okay, so these are the values. And what you can notice is that the standard error they're all very, very close to one another. Okay? By the way, don't have to type this, I'm just going to do it real quick on the side. We know that this shouldn't be the case. We know this shouldn't be the case because we got a lot more variance on the day 3 things than we do on the day 1 things. So it doesn't make sense the precision on those estimates should be almost identical. By the way, why are these not all the same number? They always end up being exactly the same number if you have the exact same n per group. In this particular data set, we don't have exactly the same n per group, and so they all end up being a little different, but not different enough to reflect reality. Right? This is probably not very, this is extremely approximate at best. Now what we're going to do is I'm going to go ahead and do linear regression. Okay, we're going to use the, you don't have to type this word out, but well, let's say the equal variance violation correction. This is that HC estimator from that one package. Again, you're going to use this vcov HC function from the sandwich package. You can read, it's this thing. It's where the estimator comes from this big ugly thing. This is something that is described in a bunch of different papers, and you're welcome to read these papers to decide how it is that these researchers decided that this was a good correction on that estimate. For right now, we're just going to believe. Okay, so we're just use the default value and believe, and then we'll compare that to our bootstrap, which we know how that worked at least, right? Okay. So I'm going to go ahead and copy this and paste it, but then I'm going to replace some things. I'll call this SEHC for the sandwich heteroscedasticity consistent estimator. Only thing I have to do is go right to the middle part here and just change this vcov function to the vcov HC function. Okay, cool. So if I run that, we can compare. Okay, So now you can see it estimates, this estimator does a better job at reflecting reality because it estimates poorer precision on the day 3 time points, which we believe to be the case. Okay, so this does a pretty decent job of at least our intuition. What's up, Josh?
Oh no. On the right hand side, I see a name of like a professor that I know.
Oh, that you know?
Yeah, Vasconcelos. The second one, Vasconcelos. Yeah. Yeah, right
Oh,
there.
Vasconcelos.
Huh?
Vasconcelos.
But I'm just wondering if it's the same Vasconcelos at UCSD.
Oh, I don't know. That's a good question. Yeah, you have to ask. You'll write him in. Go and read the paper and write him in. Okay, the last one we're going to do. No, you're good. I'm going to go ahead and copy this, and we're going to do the last one is equal. We're going to do the bootstrap variance. Bootstrap, or call it the bootstrap estimation. Okay? And for that, we're going to change this vcove thing here. We're just going to go up here and copy our boot VC. This thing. Okay, because this is the one we empirically determined with 100 bootstraps. Let's see what that looks like. Oops, oh, my bad. I'm going to change this variable too. We'll call it SE boot. Keep them all separate so that it doesn't overwrite anything. So let's see what that looked like. And that is pretty close to the sandwich estimator, actually. It's very, very similar. Like this is 1.05, this is 1.10. This one is 5.78, 4.98. These are all like within a unit of each other. They're all pretty close. Okay, so it does a pretty good job. Now, if I went back and I changed my R to something higher, it would probably start to converge on that. So let's make it 1,000 and you can see what happens. I'm just going to rerun everything. Let it run 1,000 times. I'm not going to do much more than 1,000 because model fits take a lot longer once you start getting into the 10,000, 100,000. Now I did 1,000 boots, and you can see it's starting to converge even closer. So this was what it was at 100 bootstraps. So like, let's pick this one. This one's 5.78 versus 4.98. Now if I do 1,000 bootstraps, it's 5.78 and 5.52. Okay, so it does a pretty good job. And by the way, you can use this same thing for any hypothesis test you might have, right? Because a hypothesis test is just subtractions of rows of X, like to create a hypothesis test. Let's do this just, if you give me like 2 minutes, let's like do one last thing. And that is, let's do a simple set of like 2 hypothesis tests, okay? So let's make a hypothesis test set. I'll call it CX here. Which ones do we want to compare? Let's compare the WY778 to wild type on day 1. Okay, so which rows of X is that? That's X row number 4 and X row number 1, right? The 4th row minus the 1st row. Does that make sense? Okay, cool. So I'm going to say, I'm going to use the rbind function. We're going to just stay with me. That's going to take different vectors and stack them together like rows. So the first one we're going to call, let's call this WY778 versus wild type is X row number 4. Oh no, not row number 4. Okay, oops. X row number 4. And if you just want to watch for at this point, because this will just be in the code, you can, versus X row number 1. Okay, this is the difference between the WY778 mutant on day 1 and the WY778 mutant on day on day 1 and the wild type on day 1. Cool. Let's do a different mutant. Let's do that outcrossed mutant. That's row number 6, right? So we'll call this one outcrossed for OC. That's the 6th one. Okay. And then lastly, let's go ahead and do the WY778 mutant on day 3 versus the wild type on day 3. So that's row number 10 minus row number 7, WY778 versus wild type day 3, or 3, is X7 minus, or excuse me, X10 minus X7. X10 minus X7. Cool. Great. So now, let's run this. Okay, so CX is a matrix of hypothesis tests. Now, let's look at just the first one, just to make sure we make sense. Remember, the WY778 mutant, just that regression coefficient all by itself, that represents the difference between that and wild type. So you can see that one's just a 0 on every coefficient with exception of that one, right? So that's pulling out just that value. It's not really doing very much. The last one, I think this one here on day 3, that's a calculation of 2 different ones. It's like 1 and this one is over here. Fine. Okay, great. So now let's go ahead and run the hypothesis test, right? So we can use the multcomp package to do that. So I'm going to go ahead and run hypothesis test as glht, okay? And we'll do the model where lin, if the linear factors, whatever, is equal to this cx vector. So this is the one that is baked into linear regressions. Using this one is going to use the standard errors that come from this first one, this vcove. Okay? So if I run this, okay, and then run a summary of that to look at it and inspect the results, you'll see that it has 3 values. Okay? Oh, my bad, over here. 19, so there's a difference of 19 or whatever. This is again, the distinct difference that we have is on day 1, there's that difference of like 20 or something. And then it has not really significant differences in the other 2. But one thing again to notice is that the standard error of each of these is almost identical, right? That's not exactly what we believe should be the case. Let's go ahead and run ht.hc, let's call it, is glht model cx, where the vcove now function, we're going to use vcove hc. Okay? Okay, so now if we look at that, that has different standard errors, same result, same overall interpretation. But you can imagine, remember, the standard error is the denominator for the t-test. So depending on how much you violate your assumptions, if you change that that denominator, you're going to change this thing and change your p-value interpretation. So keep in mind how much your data are skewed away from that assumption. Because you can imagine here, if these numbers were just big enough, it might be the difference between something giving you a significant result versus something not. So that denominator matters a lot. So if your data are really violating that heteroscedastic assumption, like it's not a good idea to use the built-in standard errors at all. Okay, so we have this. So we got 2, 1.1, 6.45. Cool, love that. Let's do one last one, which is ht.boot, which is glht model lin equals cx, where now the vcove is going to come from our boot vc. Okay, so rather than using a function, it's going to use that matrix. And what we just learned from before is that all of these 2 guys were fairly similar when it came to the standard error of the means, right? So they should probably be fairly similar when it comes to the hypothesis test. So if I look at the summary of htboot, we find that indeed those standard errors are very similar. So the standard errors for this hypothesis test is 2.04 using the sandwich estimator, and using our bootstrap is 1.9. It's very similar. And this last one here has a wider standard error on day 3, 6.2 or whatever. Here it's 6.45. They're both very similar. And the overall interpretation of the result is, again, basically the same. Okay? So in this case, we could have just used Josh's favorite professor's method instead of using, oh, it's not him? OK. We could have used Josh's favorite professor's method for doing the standard error thing and called it a day. But if you were, I'm just saying, if you were these people, OK, they developed methods that only apply to linear regression. OK? You might be fitting another kind of model and doing another kind of hypothesis test where you don't have those tools at your disposal, in which case a resampling method might be a tool that you want to use. So you might be doing a different type of nonlinear regression, an empirical model, some sort of other machine learning model, like something else, and you want to have some hypothesis test, some error estimation, something on it, right? Some bagging. You might want to come up with a better prediction by bagging, right? Do one of those things. Bootstrap resampling is something you have in your arsenal of techniques that you can potentially use to arrive at that conclusion. In this case, probably not really necessary. We could have used one of this guy's thing. They look pretty similar. But in some cases, bootstrap resampling might be the only thing that you have available to you to test those sorts of things with. Okay? And when I started teaching Maddie statistical methods early on, we did another form of resampling, which was permutation tests to develop null hypothesis. So that's the case where you can also do the hypothesis. Now guess what this is still assuming? we have better estimates of the standard error, but we still assume we can use a t-test to do the hypothesis test. What if that's wrong, right? What if we can't even do that? If you have nothing else at your arsenal, you can do a hypothesis test based on resampling as well. This, we only did resampling to estimate the error, and then we did a hypothesis test the way we always do. But you can use resampling to generate a hypothesis test. How do you think you could do that? What's one thing we did when we did the bootstrap resampling that you would want to change?
That I would want to change.
If you wanted to do a hypothesis test, you need a null distribution for a hypothesis test, right?
Oh yeah.
So how would you make a null distribution from your original data if you were resampling it?
Just use the normal. I would just use the original data set.
Right, but you're resampling. And what did we do when we were resampling? Maddie probably knows the answer. We had this thing, right? Where we respected the hierarchy in the data. If you wanted to do a null distribution, what would you do instead?
You don't.
Exactly, you would just randomly resample from the data. Right? Because if you randomly resample from the data, recalculate everything, and calculate whatever the difference between two means would be supposed to be with like randomly resampled data, that should be a null distribution. Because you've completely broken the structure of the data to do that. You've taken the bag and shaken all the marbles and just mixed everything together and pulled out a resample. So if you wanted to do a hypothesis test from this, just shuffle all the labels. Just say, who cares about, just all you have to do is you remove this line entirely. You just completely randomly resample the data. Okay. That's all. Hopefully that's fun. Yeah. Yeah, so resampling is very, very powerful, and it's nice for lots of reasons. What's up?
So with and without using that interaction thing
Mm-hmm.
to do the hypothesis test, like how would you get like a percentage of like your p-value?
Aha. So here's for example this. Check this out. You got this value of the change between these two groups. Okay? That value is 19.825. Okay. Now, let's say you wanted to see what this would be in a null distribution. Okay? You break the correlation structure in the data, randomly resample it. Then you recalculate this hypothesis test. That's going to be a range of values. This is a difference between two means, right? So what do you think that center point of that null distribution is going to be?
0.
Correct. And it's going to stretch in two directions,
Yeah.
right? So what do? You find out where your value, 19.825, lives in that distribution, if at all.
Oh, so you have to do that multiple times.
Correct. So you do that again, a set of boots simulations, like say you do it 1,000 times. Now you got 1,000 samples in your null distribution. You look at the histogram of those null distributions and you see what is the proportion of those that are at least this value or greater.
Oh, so you make your own distribution.
You make your own null distribution, correct. And then you see what is the probability of observing the value 19.825 or greater in that null distribution.
So you have like a sample error, or you have a standard error of your null distributions, and then that's how you get the
Well, you don't even need that. You just get the p-value just from this number. So suppose sometimes it's 0, sometimes it's +3, sometimes it's +5, sometimes it's -1, sometimes it's -10. Where is 19 on that? If it's off the scale, the p-value is exactly 0, because you don't have a single sample in your bootstrap sample that is 19.5 or greater. Everything is less. And depending on how much, how variable your data are, what the size of the effect is, 19 might be in the distribution, right? So there's going to be a probability of observing that value of 19 in your resampled distribution. Whatever that value is your effective p-value, right? What's the probability, if you completely shuffle the data, of observing a subtraction of two means that is equal to 19 or greater, right? So you're going to end up with, I'll just do this quickly at the end here, Control A, delete. You're going to end up with a null distribution of mean of WY778. But of course, it's fictive WY778 because you've reshuffled everything. You've just randomly reassigned those labels, right? You just completely randomly resampled it. 778 minus mu wild type. So in the null distribution, that's going to be centered on 0, right? And it's going to stretch out in some, this is ugly distribution, but stretch out in some directions, right? So now you have your value of 19, your point value. You're like, where is it? Is it here? So you calculate the p-value you always would. You don't even have to calculate a t-statistic. You don't have to use the standard error at that point. You're just like, where do I find this point value in this distribution?
Or don't you need the standard error of your null hypothesis?
No, because your null hypothesis could just be on the same scale that this already is. The only reason why you divide is to get everybody on that t-score scale.
Oh, so you use the standard deviation of your null hypothesis.
You don't need it. All you need is to run the bootstraps over and over again and calculate the values of the difference of those two means. You don't really need another metric. Why is it so? Okay, why do we take my? So I have my difference between two means, mean A and mean B. Okay, and I divide that by the pooled estimate of standard error, right? And that equals t. Why do we do all of this? What does this do? This gets everybody on a standard score, right? That no matter what kind of data I'm working with, whether they're inches or seconds or anything, they all converge onto this score that we call t that has a distribution. And we say in that t distribution, what is the likelihood of seeing a certain value? But when you do a resampling technique where you've just randomly reshuffled things and recalculated this estimate, you kind of don't need to do that, right? You don't need to do that at all. You just need to know what the distribution of this thing is, right? Because it's specific to your data already. You could calculate this and divide it and have like a t null that you come from, but you could just figure out what this is and plot that and figure out where your value of 19 lives in that, right? That's good enough, in my opinion.
I'm saying to figure out where the 19 lives in your...
You just say, no, okay, you have, all you have to do, it's much simpler than what you're doing. You don't need any standard deviations or anything, right? You have a number of values in here. What if occasionally you got a 19 and a 20? So what is the number of values greater than or equal to test value divided by the number of boot samples? Done. It's literally the frequency of observation of that statistic in your distribution. That's all you have to do. There's nothing to it.
Okay.
You got 1,000 numbers. How many numbers in that 1,000 numbers? Right? It's just it's a frequency, it's a probability that is assumed to be the frequency of whatever it is in your null distribution. Your null distribution is now not a function anymore. Now it's like a literal, tangible thing you have in a bag. You have every single sample from your null distribution that came from your bootstrap resamples, right? So when you do that, you just say, and if you wanted a two-tail p-value, you could say multiply it by 2 on each side, because it's probably symmetrical, although it's possible when you do resampling that it isn't symmetrical, and then that can account for that, which is something that resampling can account for that some theoretical statistics cannot, asymmetry, right? But regardless, you can say, okay, what is the number of values that are greater than or equal to the absolute value of the test sample in your boot samples, and multiply it by 2 to account for like each end of the situation. You have a two-tailed p-value. Either way, you have your null samples in a bag, and you say how many of them are this value or greater. If it's 0, then your p-value is exactly 0. Typically, we don't report p equals 0. Instead, what we say is if p equals 0, we just say p less than 1 over n boot. Meaning we don't really know what it is, but we haven't resampled enough to give you an exact estimate, so it's less than whatever the lowest number it is that we possibly have. Right?
It felt like off, like reporting p as like a discrete value.
Meh. The integrals of some, especially for chi-square and some other things, like some of these effect sizes are large enough that essentially by your computer's calculation, it's basically 0. You can report sometimes for those sorts of things, I say p is less than whatever double epsilon, machine epsilon is or something like that. You can report, for R, we typically say p is less than 2.2 times 10 to the minus 16th or something, or whatever it is, right? Yeah. But you're right, whatever it is. But yeah, you can say that. Sometimes what people do instead of doing this, like this is my method, is if p equals 0, I just report this. Sometimes people, to avoid that problem, will say the number of values greater than or equal to the absolute value of your test value plus, they do an offset, plus 1 divided by the n boot plus 1. So you get a number that's like very tinily. So in other words, what does that mean? What does that mean? If this is 0, then you have 1 over 1,001. Fine, whatever. Okay, cool. That's all. Thanks for doing these sessions all summer with me, guys.
No, thanks to you.